So we're here to talk about the 50th anniversary of GPS. And interestingly enough, 1973 was also the inaugural year of another technology that we use very much called Ethernet, which seems to be which gets all the press, but these two technologies are very much part of our lives. So we're here to talk about GPS. And David, I wonder if you could give me a slight overview of not so much the beginnings of GPS. I think anyone can find that online, but how has GPS progressed um, over the years, and where is it today?
Sure. Be happy to. I can give you a personal experience. When I was in the Army in 1994 in Saudi Arabia, our Patriot radar systems had GPS at that point. And, to try to position where the radars were, and it was incredibly painfully slow. We had one or two satellites, maybe three back then in 1994, and you get, if you're lucky, 100 meters. We were still doing things with plumb bobs better than we could with GPS in 1994. Fast forward to today, and there's solutions out there. GPS in and of itself, we're starting to get, without any other additional aid, you're getting, sub meter down to centimeter type levels, 10 centimeter type level precision now. So it's really changed the way the world works. From anything from how do I wind up getting from A to B to actually our timing. This communication that we're talking about right now would not be possible without GPS if we weren't synchronized.
So does the improvements come from upgrades to the satellites, new satellites, or the technology on the ground, or a combination?
It's really all the above, right? We've been improving the accuracy of the satellites. There's been three different blocks of GPS today, and as those have progressed, there's been improvements in the timing on the satellites. You've been seeing improvements in the algorithms that are used to steer them, just in terms of what UTC is, and steering it to GPS time has been another thing that's been improved. But also on the ground level, the user levels, the receivers have just gotten much, much more precise, right? The technology is advanced. If you looked at our first GPS receivers, you'd have these big, clunky handheld receivers. If you were lucky, you could fit them in that. Now the technology is sitting in our phone as an afterthought. So it's really been both sides of the equation have improved drastically.
How many GPS satellites are there, and are they low Earth orbit, mid Earth orbit? Where are they?
So they're geosynchronous. Actually, I'm not sure on the actual total quality. Do you know the quantity that's flying right now?
31 space vehicles. They're all in mid-Earth orbit, and it gives global coverage 24 hours a day, 7 days a week, and we all greatly depend on those things moving around.
Well, we certainly do. Thank you, Duke, for letting us know about that. Um, so timing is a big deal. I mean, we all get time from GPS, but can you tell us a little bit more about, other than getting, the time of day, uh, what does GPS do, and how does the timing of GPS help in, in systems on Earth?
Sure. Um, so if you look at it, again, I'll go right to the positioning equation first, right? The amount of time it takes a signal to get from the satellites down to your individual position, the signal travels at the speed of light. So when you know how long it takes each one of the satellites that you're seeing to get down to your individual position, you can use some geometry and figure out your position precisely. And it's really all just a time equation, right? You're saying, I know where those satellites were supposed to be at this time of day. I can see how long the signal took to get to me, and hence I can tell exactly where I am. So on the simplest level, that's what it was designed for the military, really, way back when. But now it's just so much more. things like 5G systems have to be synchronized, right? In order to get your packets at the right time, things like that, and you really have to have everything synchronized. If you look in data centers today, they have to worry about synchronizing. They're trying to transact data, multiple different data centers, right? Multiple replications. They're trying to pull all that together as one single virtual database. In order to do that, they have to have a good reference time at each location. It's another example of using GPS. There's lots of more things as you look at the time. There's lots of industrial applications today. If you look at our critical infrastructures, another area, multiple different areas, the power grid has to be synchronized today because we have these alternate power sources coming in, and you actually have to very carefully manage the load now from the renewable sources versus the conventional sources that we used to have.
What generates the time on the satellites? How do the satellites know what time it is?
So the way the satellites know what time it is, a couple of different things going on. First of all, we have USNO that's sitting in Washington, D.C., that is our primary time reference for the GPS system, right? And that time is actually what we call an ensemble, which is a number of different atomic clocks, essentially, all put together, right? So you're comparing them all against each other. We have hydrogen masers, we have cesium beam tubes, we have lots of different types at USNO, as well as some more elaborate, I'll say, laboratory type pieces of equipment. And so USNO ensembles this. They say, they come out with one specific time base, time tick from USNO. That's our official GPS time for the world. And if you drive by the United States Naval Observatory, you can actually see that time, on an LED display right there. But anyway, that time is compared to global international time, called UTC, Universal Coordinated Time, which is on top of USNO, you have all these other locations, right? You have NIST in Colorado, you have PTB in Germany, you have lots of different locations around the world that contribute their atomic clocks into this ensemble, tell us what the time is. So you have that on the ground, and then we have this official time tick coming out of USNO. What happens then is that time tick is sent to the ground stations and relayed up to the satellites. Now, the satellites are spinning around the Earth, and those satellites, they get the time signal, and then they have to maintain it until they get their next time base. So the satellites either have cesium or rubidium clocks on them that essentially have to maintain the time accuracy they're getting from the ground stations until the next time they get an update. So that's really and those atomic clocks are not as precise as the ones on the ground, but they're still very, very stable products. And, as Microchip, we have several of them up there today operating continuously on those satellites.
Microchip has contributed to a number of articles to EU World on timing, specifically towards 5G. So let's look at that a little bit. Many 5G equipment, telecoms, they will have their networks synchronized to GPS, and sometimes the signal gets lost, and that's part of what some of the timing devices have to deal with. Can you explain that a little bit about what happens if you
Sure.
lose contact with the satellite?
Yeah, sure. So, first of all, one of the reasons why we would lose a satellite, people ask questions about why, if we have GPS, why do we have to worry about it? Well, we have to worry about it for, there's both naturally occurring phenomena, things like solar flares, or it could be if I'm traveling and I'm going under a tunnel, the signal can't get through that. But I could also have the situation where there's nefarious actors out there, right, who are intentionally trying to jam GPS. It's inherently a low signal when we get it on Earth. It doesn't take much to jam it, and more advanced operators can, in fact, spoof it, which make it look like they're doing it. So if we are jammed for whatever reason, whether it's benign or nefarious, when we have jamming, we've got to come up with some way of providing that time. And what we do is we use atomic clocks or, maybe quartz crystal oscillators as well, as backups. Essentially what we do when the signal is there and it's healthy, we steer these clocks to the signal coming off of GPS. So they know what time of day it is. And they also know how much they're differing from it, right? So they get a time coming down from GPS constantly. They're also providing their own time. That quartz oscillator might be vibrating at 10 megahertz, or, an atomic clock might be, sitting there, operating away at 9 gigahertz. Whatever is going on, we compare the performance of that clock on the ground and how it's drifting to GPS. And then when GPS goes down, if it's detected that it's down or it's detected that it's spoofed, we essentially have these slightly lower grade clocks than GPS, that are going to remember what they did in comparison to GPS, and they're going to make their best estimate then based off, their own clock plus a conversion rate that they got from that error while they were tracking the whole time. And that's how we move along until we have GPS coming back. And again, it depends. In a 5G network, you actually have atomic clocks that are very, very stable, or cesium references that, in fact, that individual clock there might be able to operate for, there's a new specification coming out from ITU that, we're talking about 40 days holdover, having a total of 100 nanoseconds now stability over 40 days, which is really incredible. It's very precise, but, that's for the extreme Cadillac version, right, of what you could do. If you look back at something more like, maybe you have someone who's got, an individual cell phone tower someplace, that individual receiver is not going to be able to, it's not economical to put that level of atomic clock at each individual tower. So the tower might have something like a quartz crystal oscillator that maybe can do something like 1 microsecond over 24 hours as a common goal. And the quartz couldn't do that on its own unless it was learning when it was actually on GPS. Those error corrections are then used with the quartz to try to get us into that 1 microsecond region.
How does the time in a network, once you've got this time, and let's say you've got connection to GPS, that's okay. How is that time then distributed to different parts of the network to keep them synchronized? And if you've got your reference, that's great, but you now have to get everything else synchronized so that data arrives when you expect it, um, and what time it arrives. How does that synchronization work?
Sure. So the most common way that systems are synchronized today in a 5G network is through something called Precision Time Protocol, or PTP, which is also known as IEEE 1588, which is the standard. Basically, that is timing over packets or timing over Ethernet. So what we do is we actually send a message out from, where the GPS receiver is, to the other locations, packet-based signals, that go back and forth. And what happens is you actually have kind of this time difference, time of arrival thing. We'll send a stamp out saying, here at the GPS station, I know it's time A, right? And then that is received further downstream where they say, okay, I received time A and I see it as time B. Then they send a Ethernet signal back that says, hey, time B, I saw your time A is this time here. And eventually, through some simple math, talking back and forth over the Ethernet, you can get the precision very, very accurate, below, into at least the tens of nanoseconds right now is what we're achieving with PTP in some applications.
Is that synchronization, or is that timing in general, ever good enough?
There's, a push to get us below 1 nanosecond, right? And really, some of those applications of getting to that sub-nanosecond technology, you look at things, they talk about things like having doctors operating on you remotely, clearly you want his time to be as real as possible as to what he's doing. And that may not actually be the best case of why you need nanoseconds, because he can't respond in nanoseconds, right? His neurons aren't going to respond that quickly, but it still gives you an idea of the critical applications that are coming. Will timing ever be good enough? That's a common question that they're asked. I don't think we'll reach an answer on that. Technology is always moving forward. I think there were lots of people who said back in 70s, when we had network time protocol first being spit out, or oh gosh, I have 1 millisecond. Who the heck ever is really going to need 1 millisecond? We developed the technology, the applications are finding it, right? So I think we'll continue to see that push. I think you'll start seeing sub nanosecond solutions being more readily available. There's some boutique solutions, I would say now, that national physics labs may be able to communicate amongst themselves in sub nanosecond precision. I think you'll see that more readily available to public applications or private applications within the next 5 to 10 years. And so GPS, they just released some of the newer technology there, M code. There'll be a block for at some point. I don't know if that's going to be 5 to 10 years, to be honest. And I think what you will see, though, is actually somewhat of how can we supplement GPS. I think there's going to be a lot more focus on these alternate solutions to both provide situations, to provide timing and positioning when GPS is out, but also to improve the precision as well in some cases. So I think that's really going to be the focus in the next 5 to 10 years in the satellite-based timing world.
What's microchip's role in terms of GPS, 5G, and other timing situations?
So, we sit on a number of different standard boards. So we help steer the industry as to what's possible, or what we can do based as the timing groups. And that's not just our clocks, our atomic clocks or quartz crystal oscillators. It's also our network synchronization capabilities, some of the PTP systems that I was describing. We sit on a lot of these industry boards to help steer what can be done. We also hear what the users' applications are, try to figure out what the next solution is, right? So we're there. We're helping the industry define what can be done. We're also hearing what they need to be done and coming up with newer solutions. We're working on high accuracy PTP solutions today that are moving, maybe order or 2 orders of magnitude improvement on what we offer with our standard stuff today. That's anywhere from the distribution to repeaters, relay stations. All these different areas are what we're contributing in the 6G GPS. We're heavily involved, with some newer projects coming out that are based on alternate solutions, right? Alternate timings. We're talking to a lot of these people. They, at a minimum, they still need their accurate time basis. And we're coming up with newer atomic clocks in the future that'll be smaller in terms of weight and power, that will provide people, some capabilities that aren't out there today. So,
David Chandler and Duke Buckner, thank you for taking the time to speak with us today.